Now, if we have a small region, which I'll designate by R, delta x by delta y, bounded by a curve C, the type of region that we've just considered, well, first we can say that the integral of f dot ds around this curve, whatever our vector function, if the vector function is mi plus nj, then the boundary, or the integral around the curve, the integral around the boundary is m dx plus n dy, and that's approximately equal to the integral over the region with respect to the area of negative mx plus ny. We assume that this is so for some larger region surrounding this small region, and that we can therefore build a larger region out of this small region. And if we integrate, for example, around another rectangle that shares a side with our first region, the integral over the top part of the first rectangle goes in the direction opposite the integral over the top part of the second rectangle, so that these two contributions, these two parts of the integral, these two, let's say, contributions to the integral over the entire region are equal and opposite. The result then is that if we want to integrate over this larger region that we've just created by putting together these two smaller rectangular regions, we can say two things. The boundary of this larger region can consist of this part of the curve, this side, if we wish, of the first rectangle, this side of the first rectangle, then this side of the second, this side of the second, this side of the second, and this side of the first, so that the boundary includes all the sides of these rectangles except the one in the middle, for which the integrals are equal and opposite, so that the integral over the large region, we can say for the two regions, the integral over the curve, combined curve, we'll call that the combined C, the combined boundary of these two, of f dot ds is equal to the integral over, let's call this region now C1 and the curve C1 of f dot ds plus the integral over C2, with the integrals over common side the integrals over the common part of the boundary are equal and opposite. So the integral, and there's an f dot ds in here, writing it very small, because the main thing is just that this boundary here consists of this boundary plus this boundary. And it should be clear that the integral over the area of this region plus the integral over the area of this region adds up to the integral over the combined region. So, since we've called these curves C1 and C2, let's call this region R1. So I can say that the double integral over region 1 plus region 2 of negative mx plus ny dA is pretty clearly equal to the integral over region 1 of negative mx plus ny dA plus the integral over region 2 of negative mx plus ny dA, meaning that since the integral over C1 of the f dot ds is equal to the integral over region R1, and the integral over C2 of f dot ds is equal to the integral over R2, that this integral has to be equal to this integral. This and this have to be equal, which says the integral of f dot ds over the combined C, let's write the word combined in here to be sure we understand that, is equal to the double integral of negative mx plus ny dA over the combined region. What we want to do now is try to apply Green's theorem to an arbitrary region R. Now there are conditions on this region. Mainly it has to be simply connected. So we might say it's a simply connected region. Basically, it has no holes. If we cut a hole out of this, the theorem no longer applies. We can break this larger region into a series of smaller regions. Now I'm going to break it just into a few smaller regions using a grid. Obviously we could break this into a larger number of small regions, a very large number of small regions if we wish. Okay, on each of these regions we agree to integrate in the counterclockwise direction. So for example, over this region we're integrating over the rectangular borders of the region, over the straight line borders of the rectangular region in this direction, so that for this interval we'll be integrating again counterclockwise. So if we integrate over this region and add to that the integral over this region, we get the integral over the entire region as we saw previously. The contributions to the integral in this direction when we do this region and in this direction when we do this region add up to 0, and we end up with only the contributions of the outside of the combined region. And the same is going to be true if we go around a third region and another region and another region and another region. Along each of these boundaries we have integrals in the two opposite directions. So the integral on this boundary, the integrals, the contributions of these two integrals give us equal and opposite contributions here. The integral on these two regions give us equal and opposite contributions here. We get equal and opposite contributions here. Similarly, along this border, we have a contribution in this direction, contribution in this direction, etc. So all the common borders make contributions that are equal and opposite to contributions from other regions. So the integrals along, the net integral along every common border is going to be 0. Now we have another region here that has a common border, another region here that has common borders. All the rest of our regions, though, well, let's go just a little further. These are our interior regions. All the other regions have a side that goes along the boundary of our larger region. So if we do the integral along these remaining regions, and let's designate those as such, I'm not going to draw them all, but we get a pretty good representative sample if we get these few. Okay, all these common boundaries are equal and opposite. We're left only ultimately with the integral around the entire boundary curve C. Everything else goes away. So that what we end up integrating is just this and this and this and this and this and this and so forth. We're just integrating around these outside regions. All of the inside regions, all the inside boundaries give us equal and opposite contributions. Now, I dislike the word cancellation, but effectively what's happening then is on any of the interior boundaries, on this one we have the equal and opposite effects. They effectively cancel. Here, same thing. Here, the same thing. Here, 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 here. Along all of these boundaries we have this cancellation. Okay, so I've gone through and crossed out the boundaries on which we have equal and opposite contributions from adjacent regions, and we see that we're left only with the sections of the curve, the portions of the boundaries that constitute the boundary C of our larger region. Now I've written a few more things in here. What we're going to do is we're going to use a little notation. When we subdivided our big region, our original region, we divided it into smaller regions, and I'll call those regions R sub I. And those regions have boundaries that we'll call C sub I. So there are n small regions with n small boundaries, I being the index of a typical region and its boundary. Now, all boundaries interior to R get integrated twice. And I should maybe say all sub-boundaries. That's not a completely rigorous term, but I'm meaning the sides. Each of these regions has 4 sides, and every side that's interior to the region gets integrated twice in opposite directions, then with net contribution 0. The only thing that's left is the part of the boundary the net part of the boundaries of all these regions that coincide with the boundary of our original region. So we can say that the integral of over C of f dot ds is the sum of the integrals over Ci of f dot ds. And Green's theorem holds for each of these interior regions, so that that's going to equal the sum of the double integrals over the region R sub I of negative my plus nx dA. And when we add up the contributions of this expression over all subregions, we get then the integral over the entire region of negative my plus nx dA. And the fact then that this is equal to this establishes Green's theorem over the entire region. And we've seen then how this phenomenon on 2 adjacent regions, where the integral over the boundary of the combined regions is just the sum of the integrals over the boundaries of the individual regions, yields Green's theorem for a combination of 2 small regions, leads us to the similar conclusion over a sum of a lot of different regions. Now, there are details. This is a conceptual outline of how the theorem is proved. Your textbook proves it more rigorously and states the conditions on the region very clearly. But this is the general idea, and this is why Green's theorem holds. holds 4 simply connected regions in the plane.